Hey, Connor? Okay, so today is the third lecture of the Distinguished Lecture Series with Alex Lubotzky. So the title of the lecture is High Dimensional Expanders in Mathematics and Computer Science. So the first two lectures were between group stability and CS testability and group approximation, and today is topological expanders.
Thank you. Now, what's the rule? The 10 minutes of the eating was instead of the talk, or I can take because I hardly will manage to do it in 60 minutes. I have quite a lot to say today, so I'll get right to the point. The subject of today's talk started in the 80s in Budapest, where two undergraduate Hungarian students proved the following theorem. This is Boruss and Furedi. Nowadays, both of them are quite well-known mathematicians, computer scientists. They proved the following theorem, that instead of writing it, it will be much nicer to draw it. This was a conjecture of Erdős, and the conjecture say, assume you put in any way n points on the sphere, on the plane, and then draw all the possible triangles among them. Okay, if I will continue to do all of this, I will not finish in 60 minutes. So let's write it anyway. So we have a subset of R square. The size is n. Then there exists a point z in R square, which is covered by at least 2 over 27, to be a little bit more precise, little o of 1, just to make sure that n choose 3 of the triangles. Right? I can put n choose 3 triangles on these n points, and you start to put them all, you see that doesn't matter in what way you put the points, you can there is some kind of intersection of 2 over 27 of them. There's a point covered by 2 over 27. Very shortly after that, Barani prove an higher dimensional version. There exists CD greater than 0, such that for every P in R to the D of size n, there exists Z in R to the D covered by at least CD proportion of the simplices determined by this P, right? Every D plus 1 points determine a simplex, and then there is a positive proportion of them always intersect. That's kind of beautiful nowadays. It's kind of some of the basic results in a convexity theorem. The amazing thing, by the way, what? If D is less than 1? Yeah. No, CD is positive. Yeah, of course less than 1. You don't expect that all of them intersect. But bigger than 0. And by the way, CD goes to 0 when D goes to infinity. The amazing things came in the around 2000 and something, when Gromov proved an amazing theorem. Let's look first at the picture. If you look at the picture here, then you know I was lazy to put all the triangles, but if I would put all the triangles, then you know you start to see that there are many and maybe that area, like this area, will be covered very heavily by triangles. Gromov said, let me do it first in the picture, I allow you to put, you will put the n over choose triangles, but not by straight line. Do it in any way you want. By continuous line, but not by straight line. So I would say that the theorem, I want to avoid the theorem, then I would say I would start to do the triangle to be very, very narrow. Will be like that, okay? And then I will try to do everything. Okay, you understand what I mean? I can really arrange that all the triangles will be extremely narrow. Okay, even to avoid completely this point. Gromov says no, it won't help you. The theorem is still correct. It's kind of amazing, right?
Still with a constant.
What?
Still with a constant, but the constant may be different.
The constant is 2 over 27 for 2. And for higher d, it did it with a constant better than what was proved by Barani for the straight line. It's Gromov in his just unbelievable. To be honest, when I stated the first, I had the feeling I started to do pictures. I thought it cannot be true. But you see, the point is the following. Why eventually it is true? Now, that's completely not the proof. You see, you start to do it very narrow, right? You kind of push all of them to this area, but if you push all of them to that area, then the point covered by them will be there. What's the point somehow? That, you see, once you make a line between 2 points, you cannot change the line in every triangle. That line is the same one for all the triangles on that line. So if you want that all the triangles on that line will be very close to it, then suddenly you are there. But you may think, okay, for the other one I will do it there. No, it doesn't work if you push everything. So he did, I'm not going to write it even. You understand? You understand. And you understand now, he proved the general theorem for every D with some constant CD prime, which were better than what was known from the proof of Barani.
You mean you choose two lines connecting pairs of points?
You-
And from these lines you build,
Determine is right.
and then this is.
Right. But it was kind of an amazing results of Gromov. When you look at it, you know, Gromov is the greatest, but his style of writing is not the best. So when I look at the paper, I thought really there is a mistake. It couldn't be true, and you start to draw, and afterwards convince you that it might be true. That it might be true. Anyway, I'll say something about the proof later. Let's continue. But because Gromov made another point in his paper that we should not think of it as a property of R square or R to the D, we should think of it as a property of the simplicial complexes. Let me explain now. So I think I will erase all this. So he said, so because in this talk I will need simplicial complexes all the time, let me for a minute be a little bit formal. What is a simplicial complex? Let V be a set, usually finite, and X is a subset of the power sets of V. Sub is a set of subsets of V. So simplicial complex is such that if sigma is a subset of tau, and tau is in X, then sigma is also in X. So simplicial complex, I'm defined now very formally, is a collection of subsets of a set V, which is closed under inclusion. Now, if sigma is in X, the dimension of sigma is the size of sigma minus 1. Right? So if I have 2 points, this is an edge. If I have 3 points, this is a triangle, etc. Of course, I'm going to be very formal here, but of course, we think about the simplicial complex also as a topological object, right? Or geometric object, right? We have points, we have lines, we have triangles, pyramids that we can put in. And now, assume all the time that what the mathematician call pure and the computer scientists call it uniform is pure, i.e. all maximal cells, so sigma in X is a cell, all maximal cells are of the same dimension. The same dimension, that way I'll call it D. This is the dimension of the simplicial complex. Now we denote Xi will be the set, the collection of cells of dimension I. Okay? Now, Gromov define what is epsilon, he call it overlapping, epsilon overlapping of simplicial complexes. Later on, I allowed myself to call it geometric expanders and a topological expander. For reason I will and it seems like the community was willing to go with it, and now most people are calling it like that. So let me right away use this terminology, which is maybe not the original terminology of Gromov, though the connection with expander was certainly very much in his mind. So definition, we fix for a minute epsilon greater than 0, and we fix d an integer, and we say x is a d-dimensional simplicial complex, is epsilon geometric, respectively topological expander if for every map from X to V, from V to R to the D, I send a point to R to the D-dimensional space, and then for every F tilde, which is an extension from X to R to the D, for every affine, respectively continuous, just a second I'll explain, continuous extension out of D. You see, if I have a map from the vertices to RD, I can continue it in an affine way, essentially in a unique way. If I have an edge between here, I just put the line, right? If I have a triangle, I just put the triangle inside. But I can do it also in a continuous way, which is not necessarily affine. For every affine or respectively continuous, then it will be topological. There exist, maybe I should call it, no, I'm sorry. Let D be it, sorry. No, here is the, sorry, let epsilon go 0. We said this, I'm sorry. Epsilon expander, there exists a point, there exists Z in R to the D, covered by epsilon of the top cells. The chamber, sometimes people call it, or the top cells. You see, I take the cells of the top size, and I look at the image of them. Let's say dimension 2, the image of the triangles, and then we say that there is a point which is covered by epsilon proportion of the cells. Is it clear?
So F tilde should be into R to the D?
Yeah, of course, you're right. Sorry.
What do you mean by continuous?
That says, think about X also with a topology, right? X is a simplicial complex. I define it formally, but I said you can fill it in.
Okay.
You can fill it in by lines, by triangles in an affine way, and then you have a topological space, and now you take a map from it to R to the D. Okay?
You assume this is connected somehow.
I assume it's connected. It's not necessary. I'll say in a minute, but Usually that's what we can. Okay, so is it clear? So now you can see from here that the theorem of Borosh-Furedi, or if you want, the Borosh-Furedi and Barani, is really the statement that if we look at K, the dimension D, N, to be the full D-dimensional complex on n vertices, then KD is epsilon geometric expander. Right? That's exactly the meaning, because you take all the possible triangles on all the possible cells on every D plus 1 points. Right? This means that you take the full D dimension. It means that you take all subsets of size D plus 1, right? And every map of it, which is affine, right? There is a point covered by them. Our epsilon geometric expander, and the epsilon is this CD that we had before, or some epsilon. Right? And the theorem of Gromov, they are even topological expander, which is of course much stronger. Okay. Now, what's the connection with expander? Somehow I managed to give a talk, almost three talks about high-dimensional expander without defining expander. I tell you the truth, I did it purposely somehow. I'm sick and tired to talk about expander. I talked so much about expanders in the last 30 years, and I decided I feel here among friends, so I decided to do it a little bit, and expander got so much attention. But anyway, you don't have to. Let me actually recall now the definition of expander just to justify the name. What is a graph? If X is a graph, so a graph is a one-dimensional simplicial complex. H of X, sometimes called the Chigger constant of H, is the minimum between the size of A and its complement over the minimum of A, the size of A and its complement, the minimum over all A, all the subsets, proper subset of the vertices. Which means, if the Chigger constant is positive, like, we don't care in all this kind of thing. Okay, here connected is important, otherwise it will be zero. But if a graph is connected, is always the Chigger constant of it is always positive. But what we care is not about a single graph. We always care about an infinite family of graphs. So infinite family of graphs will be expanders if they have the same positive Chigger constant. What does it mean? It means that if you take any subset of A, which is not too small, if it's too small, take the complement, then the number of edges from it outside is at least linearly proportional to the number of in A. Okay? Sometimes people say take A to be less than half, so it's proportional. So this is not an expander. You see, graph like that is not an expander because I can take A here to be large and A bar large, and the number of edges is small. So the expander is kind of fat and round. And that's extremely important in computer science. You can imagine why for a communication network, for error correcting codes, for everything. So now why we call this expander, like the topology? Because think about, let me show you the topological expander or geometric expander, doesn't matter, one-dimensional, expander graph are topological expander. Why? You can see? So assume I have one-dimensional simplicial complexes which are expanders in this sense. I want to prove that topological expander. What does it mean? It means that I have a map from the vertices to the real line. So I go to the real line is here, and I send the vertices to the real line, I don't know where, like here, whenever. These are the input points. Now I continue this in a continuous way to a map from the graph. Now let's now choose Z, the point that should be covered. Choose it, count how many to the left, how many to the right. Let's say that this, I will choose this to be Z. Now in any map from the graph so let this be the set A in the graph. More or less half. So now every line from A, every edge from A to outside A must go to this point, to Z, by what is called intermediate value theorem in calculus, right? Just by intermediate value theorem, it must go. Now, because we know there are many edges going there, this is a topological expander. Okay, but now, in the theory of expander, those who are familiar with this, to prove that the complete graph is an expander is an exercise for a fourth year elementary school. The complete the expander. The whole point of the theory of expanders, which is a huge history, is about proving that there exists and construction of a K-regular expander or bounded degree expanders. Now, the theorem of Gromov here, which is very deep, very difficult, but what is about? About the analog of the complete graph in the higher dimensional, right? So Gromov put forward the basic questions: are there bounded degree geometric and topological expander in I dimension? When we say I, even dimension 2, 3, or any dimension, when he started, he didn't know. But few years after that, something around 2010 or something like that. So I want to erase all this. A paper came out by more or less all the great guy of convexity and combinator, or this type of, together, 5 authors, to prove theorem. This was Jacob Fox, Gromov, Laforgue, that this is not the Fields medalist Laforgue, it was his brother, though Vincent Laforgue, but the name of Laurent Laforgue will also come up soon. Our Asaf Naor, and the Hungarian guy. They prove there exists bounded degree geometric expander. So for every D, we bounded degree D-dimensional geometric expanders. They gave 2 proofs. In fact, Asaf told me that they have even more. They included only 2 or 3 proofs in the paper. Proofs. One is random. In a proper talk, I really had to present a model, but it's if you go home and you will think for a while, you may come up with this model of random bounded degree, which generalize some classical model of bounded degree graphs. You can do higher dimensional version. They prove that they have this property. And the other properties, they use Ramanujan complexes. And now I'm going to give you, in 3 minutes, a subject of 20 years. So I define expanders. It's well known that expanders has a spectral meaning by eigenvalues of the graph. And in the 80s, Peter Sarnak, Ralph Phillips, and me, we constructed what is called a Ramanujan graph. Ramanujan graph, even without giving the precise definition, are graphs which are in some sense optimal expanders. The specific one that we constructed, people now call them usually LPS, are giving us a little honor for that, were constructed in the following way. We took the Brouwer-Tietz tree that I mentioned yesterday, which is the symmetric space associated with the p-adic group SL2QP. This is an infinite p plus 1 regular tree, and we divide it by the action of congruent subgroups of some arithmetic groups. Maybe this all this means nothing for you. Our work was not that deep. Our work used extremely deep theory. It in particular used the work of Deligne in characteristic 0, or if you want in characteristic P, Drinfeld, on the Ramanujan conjecture, whatever it means. I don't have time to go to that. But they are kind of optimal expander. And they are called Ramanujan graph. In the around 2005, Beth Samuels, which unfortunately this was her PhD at Yale, and after a short while she passed away. It was a big tragedy. She left 2 babies. It was really terrible. And Uzi Vishna, who is now at Bar Ilan, he was a postdoc at Yale at that time. And I was kind of a regular visitor there. We used the solution of Laurent Laforgue, the brother of the Ramanujan conjecture for GLD. This Ramanujan conjecture of Deligne and Drinfeld can be expressed in the modern representation theory way as a statement related to GL2. And he proved GLD over function field. He got the Fields medal to the. By the way, notice that the young people should notice everyone who worked for us got the Fields medal. So we started to work what is the combinatorial meaning of the solution of Ramanujan conjecture for higher dimensional. We didn't have any purpose in mind, I have to admit. I'm among friends, I'm willing to admit, I'm getting a lot of credit for that. People say that I had the vision, that it's there, that it became so important. I had no vision. Beth Samuel was a student of Piatetsky Shapiro at Yale. She learned a little bit of automorphic form, but somehow she got stuck with the problem Piatetsky gave her. She came to me and said, maybe you can suggest something. I told her, Laforgue recently proved this higher dimensional version. There must be some combinatorial meaning. So we tried to play with it. It was very, very difficult. Luckily, we had Uzi Vishna, whose expertise was exactly on what we needed. We worked about it for a long time, and we made a construction of d-dimensional simplicial complexes, infinitely many for every d, which we named them Ramanujan complexes. Now, some people call them LSV complexes. And then they suddenly, few years after that, somebody told, I knew nothing about the subject, somebody looked to Gromov. They're using your work. They took the Ramanujan complexes and they proved that they are d-dimensional geometric expanders, I want to state. They resolve the problem of geometric expander, but the topological the problem of topological expander was still open. And in fact, I talked with Gromov, at that time, and it really was not sure if they exist or not in I-dimensional, because the feeling was, you see, I told you before, the feeling was that if you take the complete simplicial complexes, because you put, once you put one line, you have to take so many triangles to put nearby it, unboundedly many, right? You have to, if you work with n point, you still have like n minus 2 triangles, n minus 3 or something like that, to put on that. So it forces you to do it. But if you are allowed to do only bounded number of triangles containing every vertex, then maybe you cannot do this. Anyway, so it took us, but we got excited. By the way, I want to say, just to show you why the problem is difficult. Random simplicial complexes, at least in the model of, are not topological expander. Are not that we don't know to prove. They are not. You remember about locally testable codes? Random, that random are not. It's sort of related in a vague way to this, you will see toward the end of the proof. Random are not, so anyway, few of us started to work like crazy, and we tried to prove. What did we try to prove? Random are not, but what are yes? The Ramanujan complexes. This was the only one we knew something about. And now we prove the following very strange theorem. It's still open whether the d-dimensional Ramanujan complexes are topological expander or not. But we prove the following theorem. This was proved by Tali Kaufman, David Kashdan, and me, just for the case d equal 2, to a very complicated proof. And then after that, Kaufman and my student Shai Evra for every d. In fact, if you are interested, don't look at our paper. Because in some sense, Shai is very modest. He said, oh, all the ideas are there. It's not really true because they are so complicated and done. He kind of clean, how you say, in Hebrew say, מרוב עצים לא רואים את היער, in our paper. They did it so clearly. This paper is 40 pages just for d equal 2. This is 25 pages for all d. It's a wonderful paper. He got the Ramanujan Prize for this. Shai was still young enough to be eligible. The Ramanujan Prize only till the age of 32, the age where Ramanujan passed away. Anyway, so the theorem, but it's a bit strange, the theorem. It says the following. Given D, the D skeleton of the D plus 1 dimensional Ramanujan complexes are topological expanders. I have to express it a little bit more correctly. You have to assume that the prime number is very, very large, and etc. By the way, I want to be honest here. Again, we are among friends. The degree that we need for these complexes is so high that it's bounded degrees. But you know, the bounded is more than the atoms in the universe. so it still will be very, very interesting to find something which is more down to earth.
Does the bound depend on D?
What?
Does the bound depend on D?
Yeah, depend on D and depend on P. You see, we are using p-adic, but you have to take P large enough with respect to B to D, and then you take the Boatitz building of this, blah blah blah. But it solved the problem of Gromov, because for every D we take the D plus 1 Ramanujan, we just kind of ignore the top cells. We take only the cells up to dimension D, and these are Ramanujan. These are topological expander. Okay, let's continue because we have a lot of things to do today. I want to dedicate the second half of my talk, less than half, to give little bit review on the method of Gromov. Not really the proof of Gromov, just one of the tools that is needed. There is Amir Yudayov. I'm not sure if it was published or just put on the internet. He put a beautiful elementary kind of working out the proof of Gromov for the complete d-dimensional complex, two-dimensional complex, just in dimension 2. Just in dimension 2, so you are welcome to read it. You can even run a seminar almost for undergraduates. That's a very nice presentation. I want to talk about the machinery which came up in the work of Gromov. He uses cohomology with coefficients in F2, in the field of two elements. And I don't want to assume that you know what is cohomology. I'm going to give you a 2-minute course on cohomology of what we, and only of what we need. So I'll just do it for simplicial complexes. And F2 is much easier. So X is as before simplicial complex. You remember Xi are the cells of dimension I. We denote Ci, the co-change X to F2. Soon we will omit this and we'll write Ci. These are all functions from Xi to F2. So on every cell, I put 0, 1. That's all. This on Ci. Now, we have the co-boundary map from Ci to Ci plus 1. Namely, I take F in Ci, take delta of F, and I have to, if you want to be precise, delta I of F, and I have to evaluate it on sigma. Well, what is sigma? Sigma is in Xi plus 1. Is a cell of dimension I plus 1, namely it is I plus 2 points. Right? So this is simply sigma sum over all tau, all the walls of sigma. I take, which is basically say, take sigma and omit 1 point at a time. You get a wall. A wall is a cell. You remember simplicial complex is closed under inclusion. You get a cell of dimension I, and you sum up of the value of F. That's all. F of tau. Here is a well-known exercise that you should do once in your lifetime, not more than once, but if you do a delta of I after delta of I minus 1, this is 0. I won't do it. Here it's very easy. Usually you do it over the real numbers, and you do it with signs, etc. It's that over F2, everything is easy. So as a conclusion, the so-called BI, the co-boundary, which is the image of delta I minus 1, is a subspace. This is a vector space over F2, and now it's a finite dimensional vector space. The image delta I inside, it's inside the kernel of delta I, which is denoted Zi, the co-cycle. The co-boundaries are inside the co-cycle, and the cohomology group, Hi, is simply Zi divided by Bi. Okay, this was a 2-minute crash course on cohomology. Now, there is a lot of literature, etc., but vanishing of cohomology, not vanishing of cohomology, it tells you a lot about about this. But I want to go to a little bit more delicate information. Okay, now I tell you the truth. I was hesitating how to present it, and then I decided to cheat you. If I would not cheat you, I will need more time. So I'll say more or less when I cheat or not, but I will define definition. X is epsilon co-boundary expander. You see? Now we have another notion of expander. Co-boundary expander. Or there is also cocycle expander. Epsilon cocycle expander. If, now again, we care about a family of d-dimensional simplicial complexes if for every I between 1 to d minus 1, we'll call it hi of x. Hi of x is going to be the minimum between, now I know that I'm going to a little bit confuse you, the minimum of over all f, take all function f, which are in ci but not in bi. I tell you, please think for a minute that the cohomology vanished, that the boundaries and co-boundaries are the same. The cohomology vanished. We need the two definition, but I don't have time. I take the minimum over all function in ci, which are not co-boundaries, and therefore also not cocycle, of the norm of delta f. What is the norm of delta f? Delta f is a function on ci, right? The norm of it is simply what is the proportion of elements on which it's zero, or for which is non-zero. The size of the support divided by the number of all cocycle, of all I plus 1 cells, divided by the distance between f and the co-boundaries. See, so this is a positive number. Okay? I know that there are some differential geometry people here, Riemann geometry. This is a replacement of spectral gap if you would do it over the real. But I don't have time to explain. It's not difficult. It's kind of, if you do this, you get the spectral gap. So it's kind of a spectral gap for operators over F2. So this is the HI. Now, another little exercise, if X is a graph, and you will, 0 up to d minus 1, and you compute it for the graph, then the classical Shiger constant, this Hx, is really H0 of x. So this is kind of generalization of the concept of expander. And the big theorem, now it looks a very artificial type of definition, but it came up more or less at the same time in the work of Gromov on these overlapping properties, and in the work of Lineal Meshulam, Roy Meshulam from the Technion and Nati Lineal, who study random simplicial complexes. I don't have time to explain all this. That's actually not difficult, but you'll have to invite me again for this. Okay, so the big theorem of Gromov is if x, d, n are all epsilon coboundary expander, namely all the hi are more than epsilon for every I between 0 to d minus 1. Now this will be expander, coboundary expander, that all these numbers, the first one for graph is the classical expander. Actually, some normalization, but doesn't matter. If all of them are bounded away from 0, then X, and D are d-dimensional topological expanders. So, okay, that's the great theorem. Okay. So you see, there are various notions of expander. By the way, they are not equivalent. That's part of the problem. The one-dimensional theory of expanders, there are several different definitions. They're all equivalent. When you go to higher dimensional, you can invent your own definition. You can take even one of the definition and extend it in a several different way. And you have several definitions. Each one of them you can then, and part of the research on this high-dimensional expanders is to understand the connection between the various definitions. But we want now, okay, so now we have this. Now the way we proved that Ramanujan, the skeletons of the Ramanujan expander, we had really to work out because they are not co-boundary expander. They are something weaker, which are cocycle expanders. But we have to prove that that would be enough. Well, that's not me. It's this Kaufman and other people prove that that would be enough. The weaker property, and we could prove the weaker property for the Ramanujan, but not to the top one, only up to the top.
Could you just repeat, so what's the little h I?
So h for every I between 1 to d minus 1, I look at the minimum over, I take all functions, all cocycle, all cochain, ci, provided they are not co-boundaries. I look at the norm of delta f, namely it's basically the size of the support of it normalized, divided by the distance of f from Earth. I take the minimum over all functions. And this is the Chigger, the i-dimension Chigger constant, if you want. If you specialize to the H0, you get the classical Chigger constant.
What's the condition? So for all I,
HIX is greater than
So for all I, HI are bounded away from 0 uniformly. If you have this property, then you get topological expanders.
this is the definition of a co-boundary
Right.
for all.
For all I. Yeah, I should really say that if you fix epsilon, you say that, yeah, sorry, you are right. I had to say that HI is more than epsilon. I'm sorry. Okay. We are getting, okay, not too bad. Not too bad. So he proved that they are topological expander. Okay, as I said, we had to twist a bit his theorem and to get that this LSV, that these Ramanujan graphs are co-boundary, are a cocycle expander or systolic expander, many names coming up here. But we couldn't prove it for the last one. We proved it only up to d minus 2. For a reason that we have to, I don't have time to explain. We had to use we had to use the fact that you have d plus 1 dimension, but we could not prove it to them. Okay, very good. I want to finish with 2 remarks. Long remarks, but I still have like 10 minutes. The first remark is, look at this. Do you see here the stability? Computer scientists, are any computer scientists here? No. Do you see testability in computer science? Okay. Testability, not stability. Testability of computer science. No, okay. I cannot blame you. When I came to that, I was already been into the testability. Then I could see the stability results here. Why? I'll tell you what's the problem. It may be not an interesting problem, but I claim, okay, I'm erasing this. So now finally 2 last remark that will close the circle with all what we talked in the previous lectures. So remark A, testability. Here is the problem. Here is the problem. You always have to think that I have a huge data, n is very, very large. and I ask you, given f in Ci, I'm given a function on the I-dimensional cells. There are zillion of I-dimensional cells, right? We are talking about a huge, huge simulation complex. And I ask you, is Fi in Bi? Is it inside Bi? Is it a co-boundary? This is like error correcting codes, testability of all codes. Think of Bi as a code inside Ci. It's a bad code. It's not a good code in the sense of Shannon because you can see if you take a function in Ci minus 1 which lies only on one point, the co-boundary of it lies only in a bounded number, suppose it's very small. It's not a good code. I can still ask, is it testable problem? And the answer is, if X is co-boundary expander, in fact, it's enough to know it only at dimension I. So if Hi is bigger than 0, bigger than epsilon, bigger than 0, then this problem is testable by reading only I plus 1 points. But you see, I plus 1 bits. Why? I will take F in Ci. I have to decide what is the stability. There is an algorithm which read only bounded number of bits from F and decide whether F is in the code or at least close to it in the Amic distance, right? So I take F, I pick up random sigma in Xi plus 1, and I compute delta F of sigma. I can compute it only by reading sub cells of it, I plus 1 cells of it. I read only I plus 1, and I plus 1 is constant, right? And I'm answering yes if I get 0, and no if I'm getting 1. If I'm asking, if it is a co-boundary, then it's a co-cycle, and then of course the yes is yes. If I answer no, it must be, or it's very likely it's very far away, because the proportion delta F modulo the distance is large. Right? That's exactly the meaning of Hi bigger than epsilon. It's bounded from epsilon. Namely, the size of the support is linear in the distance of F to the code. Exactly locally testable of code appearing in this story. Okay? So this should take you back to the first 10 minutes of this series. That co-boundary by Gromov or by linear Meshulam or by us for this produce you locally testable code. Of course, it does not solve the big problem of the computer scientists because they wanted I rate and I distance, which is certainly not the case here, but the local testability is 0. And it's trivial. In fact, I can tell you, again, among friends, I don't mind to tell you. Tali Kaufman and I observed this connection, and we wrote a paper. And this is, I'm not ashamed to say, this is probably the most trivial paper I have ever written, and the most influential one at the same time. Because it's trivial. You see, we just said that co-boundary means testability. In order to impress the computer scientists, we had some examples. They don't care about this, but examples that they would care. We translate them back to this and that. I don't have time to And anyway, there are no computer scientists here, right? So I don't have to please them. But in some sense, that little paper call the attention of the computer scientists to all this co-boundary expansion, this cohomology and Garland work, and suddenly this is a big subject in the computer science community. Last remark before we finish, which is slightly more technical, but almost. What did I put? Oh, I'm sorry. Oh, thank you very much. Maybe I will erase this. More recently, like a year or two ago, I noticed with my ex-student, Michael Chapman, whose name also came here, maybe, or didn't come here, and other, we noticed that this suggests an approach to the Sophic problem. So now we have to close completely the circle of all this talk. Why? Take such a simplicial complex, and instead of doing this with F2, do it with any group, even non-commutative group. For our purpose, we really need a symmetric group, Sim n. Define maps from xi to F2, but now you have to be a bit more careful, and just assume x dimension 2. Now assume the dimension of x is just 2. I don't need anything more than that. And I want you to concentrate on C1. So I put on every edge, I put a permutation n of Sim. You can think of it as a generalization because F2 is Sim2, right? It's the symmetric group on 2 elements. But now you have to be a bit more careful. You have to look at directed edges, and you put the function on the directed edges. If you put sigma, or if you put a permutation on the directed edges, on the opposite direction you put the inverse. Okay, fine. Then you have it. You have C1. You have also C2. You can take triangles, directed triangle. You can go either this way or can you go this way. And it will be the inverse. Now I claim that you can define this delta, at least from 1 to 2. For 2 to 3 it's a problem. For 0 to 1 it's possible, clearly. For 1 to 2 is also possible. Why? You take delta I of a function f. A function f is really an assignment of permutations on the edges, right? You have to apply it. You have to apply it to sigma. You have to sum up on the edges, right? You sum according to the length, to the order, right? You sum according to the order. So if you get from one direction, you get this. From the other direction, you get the opposite.
The sum is not product.
It's a product. Now the sum is not sum, but it's a product of the permutation. And now I claim that you can even define this. But, okay, there are two natural ways to define. What does it mean, the norm of a function on the edges? Or on the triangles. One way is to do like here. Either it's 0 or not 0. Let's call it the discrete metric. Another way to define the norm of a function, or delta of it, doesn't matter, as the Hamming distance. You remember that every permutation is like a norm of it, which is the Hamming distance to the identity. And you sum up over all the two cells. I prefer the second one. I'll tell you something about the first one. So you can define this co-boundary expansion. Now, or better, here I prefer to do it on cocycle expansion. Just takes things which are not cocycle. Let's think for a moment on one of these Ramanujan complexes, even if I didn't explain what they are. If you take a simplicial complex, what is the fundamental group of the simplicial complex? You put, the generators are putting elements on the edges, and every triangle defines a relation. That's more or less the story. What does it mean to, if so, what is, now if I have a cocycle from on the, I cheated a little bit. I have a cocycle on the simplicial complex to the symmetric group, cocycle. Cocycle means the delta of it is always 1, right? The product over the edges on every triangle is 1. This defines an homomorphism. So the cocycle has exactly the homomorphisms. What does H measure? It measures if you are not an homomorphism, how far you are from being an homomorphism. This is stability, right? So if we could prove for these Ramanujan complexes that these HI are, even for one of them, is bounded away from 0, H1, for all of them together, we would prove that the fundamental group is stable in the sense that we want to. And if we would do it for this, the Lie lattice, which is not residually finite, we get an non-Sophie group. We put this suggestion to the world after, but we couldn't really do it. Amazingly, when we did it, I have to tell you, when I explained to you, it looks like, okay, it's a trivial observation. It took us 30 pages to write it because we wanted to have concept. It's just basically going over the definition. At that time, a paper by Yotam Dickstein, who gave a talk today here at the computer science department, is a candidate for a position. By the way, you should take him. I tell you should take him half position. I told you the other day. He's fantastic, and he's really a mathematician. And I think you may tempt him because I think his preference to be in both departments. But he's kind of trained as a computer scientist. He and Irit Dinur proved that this Ramanujan and all this stuff are co-boundary expander, what we need. With the sim, with the symmetric group, but with the wrong metric. Wrong from our point of view. They use the discrete metric. Discrete metric turns out much easier and it works. At that time, we were very confused. When their paper, they come, we thought, I must say it in Hebrew, I don't know how to say it in English, צדיקים מלאכתם נעשית בידי אחרים. הגמרא said. That they didn't work for us. Turns out it's not so simple. Namely, they did it with the discrete metric, we need it with the Hamming norm. If we could do it also with the Hamming norm, we would solve the Sophic problem. In the last year or two, I'm working with Dickstein, Shai Evra, with Michael Chapman. We are working all the time. Well, everyone is different. We basically, on a regular basis, we meet on Zoom. Not much progress, I'm afraid. But young people here, maybe we miss something simple. Anyway, I think that my time is over. Thank you very much for all the visit, the hospitality, which was wonderful, and everything. Thank you.